Okay. Figured this one out. I was being stupid. So, okay. So we're going back to number one real quick because I'm trying to show how if I take the sine of this angle and this radius, I'm going to get the same value as if I just took this perpendicular piece. Okay. So we had figured out what the hypotenuse was. That's the R for this point D. That's this distance. Okay. If I want to get this angle, I know tangent of this angle is 100 over 200. So 100 divided by 200 is 0.5. Okay. So then if I do the inverse tangent of 0.5, that gives me 26.565. And I'm just going to write all these digits because it helps to have all of this. You'll see in a minute. So that's this angle. This is a 26.565 blah, blah, blah degree angle. So now I'm going to take the sine of that angle. So I can get, again, that perpendicular portion of R. And that gives me this value. Then this is what I multiply by mass, still 1,000, times velocity, still 10, times my R value, and that's this hypotenuse that we got. And I wrote all these digits out here. 223.6067978 gives me that same million. Ta-da! That's what I wanted to show y'all. So that's a messier way to get to it. And that's what I was trying to show y'all in class when I had you do this activity. Okay, is that you should get the same angular momentum at each point, because each time you do that sine and get this whole radius, you're actually just picking up the perpendicular piece of that. So, okay. Got a couple of conservation of angular momentum type questions. So here we've got a merry-go-round, has a radius of 4 meters per second, rotational inertia that's given. When it is at rest, there's a kid running along. So here's our merry-go-round, okay? And we've got this kid running, and they're running 6 meters per second along a line tangent to the rim. So their velocity is tangent to the rim of the merry-go-round, and then they're going to jump onto the merry-go-round. And we want to know what the angular velocity of the merry-go-round is then. Okay. So this one we could do using kind of conservation of angular momentum. So starting off, I'm just going to use MGR for short for merry-go-round. Our initial merry-go-round angular momentum is 0 because it's at rest. Okay. Our kid, let's see, they're going to have an initial angular momentum. We can call them a point mass. Okay. So they're running along tangent to the rim. So they're going to be, like, if this is the radius, this is going to be a 90-degree angle. So that turns to 1. So they're running along, they're going to jump on. And so their initial angular momentum is going to be their mass of 19 times their velocity of 6 times the radius of the merry-go-round, which is 4. So 19 times 6 times 4, 456. So the total initial angular momentum is just 456 because the merry-go-round's at rest. Now, when the kid jumps on the merry-go-round, you got to kind of picture this in your head. It's going to start to turn, okay, because they're going to jump onto it. They're going to add angular momentum, basically, to the scenario. And so now we're going to have a final, let's say, I total final. We've got to include the rotational inertia of the merry-go-round. And now the kid is going to be like a point mass on the merry-go-round. So we'll use mr squared for the kid. So 800 plus 19 times 4 squared. We can't consider them a point mass from the perspective of the axis of rotation anymore, because now they're on the merry-go-round. They're part of the overall rotational inertia of the merry-go-round. So 19 times 4 squared is 304 plus 800 is 1104. So I'm running out of room. All right, so we're going to use conservation of angular momentum here. We got L total I equals L total F, okay? Or, all right, in this case, we know our L total I was just the kid running the 456. We know our total final rotational inertia of the two, the merry-go-round and the kid, is 1104. That would be multiplied by their final angular velocity. They're both moving at the same change in angular displacement per change in time rate once the kid jumps on there. So this will give you the angular velocity of both of them. This is like a kind of like an inelastic type collision, I guess, for angular momentum. So we can solve for this final angular velocity by taking 456 divided by 1104. And that gives us 0.413. Let's see if that's an answer choice. Yes, it is. Yay. Okay. So that's how we get. This is really a lot like the collisions we did with linear momentum, where you can solve for a missing quantity, usually one of the initial velocities or maybe a final velocity in the case of an inelastic, which is kind of what this is here, using conservation of momentum. So, all right, and then this one's also a conservation of momentum. So here we got another merry-go-round. We're given a radius, rotational inertia. It's initially spinning at 0.9, so it's moving. And then while it's moving, there's a little kid who started off sitting at the middle, and they're going to crawl over here to the rim. Apparently no one's watching them to see if they're safe. Why were they sitting in the middle of a spinning merry-go-round anyway? I have no idea. But anyway, it's a physics problem. So that's going to change the angular velocity of the merry-go-round. We want to find out by how much. So our initial, let's see, our I total initial is, or well, let's do L total initial. That's going to be angular velocity times our rotational inertia. The kids sitting at the middle, like their radius is 0, so they're not contributing to the initial rotational inertia. So we can just use the rotational inertia of the merry-go-round. Hopefully that makes sense, because in the initial point, they're not changing this scenario. They're just sitting here at the middle, okay, while this is spinning. So we can do 628 times 0.9, which was our initial angular velocity. So we're just using I times omega here to get our initial angular momentum. 628 times 0.9 is 565.2. Okay, now when the child reaches the rim, our L total final, okay, is going to be, this is going to change my angular velocity of my scenario. So I'm still going to have my merry-go-round, still going to have 628 as its rotational inertia, but now it's going to be a different angular velocity. And the kid is now contributing as a point mass here on the edge. So the kid's going to have a mass of 23 and a radius of 4 squared, because that's the radius of the merry-go-round. So now instead of contributing nothing to the angular momentum, they're like a point mass added here on the end, spinning around this rim of this as it moves. Okay. And they're also going to be moving at the same final angular velocity. Both of these are together, so they're both going through the same angular displacement. So we can solve for this by setting L total initial equal to L total final. Conservation of momentum. So 565.2 equals 628 omega final plus, let's see, the kid is 23 times 4 squared, 368 times omega final. So that's 565.2 divided by, I would factor this out, right? And so then I'd have 628 plus 368 gives me 0.567 for my angular velocity final. Let's see, that is one of our answer choices. Yeah, so we're just, again, using conservation of angular momentum to get a final velocity. I don't know, it's kind of an inelastic collision, I guess. I mean, it's really just more of a change in the scenario. It's a change in the mass distribution, truthfully, of the scenario, because you have 23 kilograms of the mass moving from right here at the axis of rotation to a distance from the axis of rotation. So now you've changed some of that mass distribution to a different point, and that's going to change the overall rotational inertia of our system here, right? That changed this from what it was to a larger value. So our angular velocity went down. Our final was lower than the initial rate at which the merry-go-round was spinning. So, okay, hopefully all that makes sense.